Today, we're going to zoom in on one single, absolutely fascinating object deep out there in the cosmos. It's a pulsar known as B2111+46. Now, you can think of it like a cosmic lighthouse, a spinning neutron star flashing a beam across the universe. And for years, scientists have been scratching their heads trying to figure out exactly where that powerful beam of light actually comes from. I mean, seriously, how do you even begin to measure something like that? It sounds completely impossible, right? This isn't like measuring a mountain here on Earth. We are talking about an object 16,000 light years away, tucked between the constellations Cygnus and Lacerta. Trying to pinpoint a specific location in its atmosphere is just a staggering challenge. So, how on earth did they do it? Well, it turns out the answer wasn't about building a bigger telescope. It was about listening more closely. The key, the secret, was hidden right there in the timing of the radio signal this pulsar sends out. It's like a secret message that's been traveling across the galaxy, just waiting for us to decode it. Now, to really appreciate just how clever this breakthrough is, we first have to understand the problem they were up against. For decades, one of the central questions in pulsar astronomy has been, where exactly is the radio signal coming from? Where in the star's magnetosphere is this beam actually born? And what they're trying to measure is something called the emission altitude. If the pulsar is a lighthouse, the emission altitude is basically how high up the tower that bright spinning lamp is located. Knowing that number is absolutely crucial for understanding how these incredible objects actually work. The thing is, the old ways of measuring this were, well, they were kind of flawed. The geometric method, for example, had to make this huge assumption about where the edge of the beam was, but that edge is super fuzzy and hard to define. And other methods, based on relativity, they just assumed the emission started at ground level, an altitude of 0, which, as we're about to see, was just plain wrong and led to some really misleading answers. And then, the breakthrough. It came from a really clever application of Einstein's relativity. A team of scientists realized that the pulsar's intense spinning physics created this tiny but totally predictable distortion in its radio signal. It was a tiny shift in timing that they could use like a ruler. Okay, so stick with me here. It's all about your point of view. If you could somehow hitch a ride on the pulsar as it spins, what physicists call its co-rotating frame, everything would look perfect. The different parts of the radio signal would all start from the same central line, all neatly aligned. No mess, no fuss. But of course, we are not on the pulsar. We're way over here on Earth in what's called the laboratory frame. And from our vantage point, watching that intense rotation, things get smeared out. The signal gets distorted, and that perfect alignment, it's gone. And this distortion has a name, the aberration retardation effect, or the AR effect for short. Here's the gist. It causes two key parts of the signal to shift in time. The main core part of the signal shows up a little bit early, and another part, related to its polarization, shows up a little bit late. And here's the absolute kicker. They shift in opposite directions by the exact same amount, perfectly symmetrical. And that perfect symmetry, that's the secret sauce. It's kind of like having two people stand back to back and then walk in opposite directions for exactly 1 minute. If you can find where both of them ended up, you can calculate the exact midpoint where they started, right? That's exactly what this new method does. First, they measure the arrival time of that early core peak. Step 2, they measure the arrival of a key point in the signal's polarization, which they know arrives late. The true, undistorted center has to be the exact midpoint in time between those two. And the size of that shift, how early and how late those signals were, that tells them exactly how high up the signal came from. It's just an incredibly elegant piece of cosmic math. Okay, so that's the theory. What actually happened when they applied this brand new ruler to our pulsar, B2111+46? Well, they analyzed its radio signal at 2 different frequencies, and honestly, the results were pretty surprising. Get this. At a lower radio frequency, 610 megahertz, they clocked the emission altitude at 503 kilometers above the pulsar surface. Just think about that for a second. A precise measurement of a feature on an object thousands of light years away. Absolutely incredible. But then they looked at a higher frequency, 1408 megahertz. And this time, the emission altitude was just 83 kilometers, much, much lower. So, what does that difference mean? This was the big reveal, the eureka moment. It's not one single lamp on this cosmic lighthouse. It turns out different frequencies of radio waves are being generated at different altitudes. For this specific pulsar, the low-frequency radio light is born high up in its magnetosphere, while the high-frequency light comes from much closer to the star's surface. So why does this all matter beyond just this one pulsar? Well, because this technique isn't just a one-off measurement. It's a completely new and much more accurate tool. You could call it a new cosmic ruler. As the scientists who figured this out said themselves, the old methods were flawed because they just ignored this emission height. But as they proved, it's a significant factor. You simply can't just brush it aside anymore. And that's the real takeaway here. Pulsars are these amazing natural laboratories for studying extreme physics. And by measuring them more accurately with tools like this one, we can test our most fundamental theories of gravity, of magnetism, of matter itself, under conditions we could never, ever hope to create here on Earth. It really makes you wonder, doesn't it? By decoding this tiny, symmetrical time shift from a star so far away, we unlocked a fundamental secret about how it works. It just goes to show that sometimes the biggest discoveries are hiding in the smallest details, just waiting for us to listen in.